Seriously?
Yes. I'm going to even asking. Yes.
People advanced. Huh? And your friends have been sending?
No.
Okay, let's do this. Let's do it. I should be there. Okay. Marvin, Peter, Angel, Simon, Julia, Kenny, her, Mano, there, Paul, and the Paul, and then there. For me, no one can be alive. Who is it? Have you time? Four, that's it. Okay. Jacob. Rashida Prince. There. Okay. This one's Michael. So the four remaining in the Cornelius Miller. The 16%. So you keep two sheets together. Okay, let's move. So here we found what 740. So if your base there is found the value of what 32,000, isn't it? Over the answer should be 740 MVA. Okay, let's move on to the last question now. Percent elongation. So you're trying to see by how, at the end of everything, you want to see by how much this particular specimen has experienced elongation, by what percentage. So there's something about the final length, isn't it, and the original length. So how do you find that percentage increase? How do you find it? minus L original, isn't it? So change in length of original right? That's question 5. Huh? So we have L final minus original length divided by original length and multiplied by 100%, isn't it? Or delta L, isn't it? Changing length over the original length and multiplied by 100%. Same thing. Changing length is that change. Final minus original. So the final length is a fractional length. After it fractures, there's no more extension. Pardon? So 40.9. What are we having here? 40.9, right? Minus 40 divided by multiplied by 100%. Okay. So what's the numerator there? 40.9 minus 40 is what? Okay, so it's dividing. So meaning even the units are dividing, isn't it? So the millimeters go, then you carry 1 unit there. What's the answer? What's the final answer? 2.25%. So if a material has a percentage elongation, see that as we go. Let's come to the last one. Let's look at number 6. I didn't write it there. Number 6 is ductility is the test piece. Ductility, you can write that down. Ductility if the test piece connects to an area of 32.3, an area of 32.3 square millimeters. Let me rub this, okay? So ductility, what is ductility involved? Percent area reduction. Okay. Percent area reduction. Have the formula for percent area reduction. So what is being asked of us here? So when you see ductility here, what they're asking for is basically you use the formula for percent area reduction. So remember, as your test piece is growing in length, it's increasing in length, isn't it? As you are stretching it out, what's happening to the diameter? It's reducing, isn't it? That is what is the percent area reduction. We're finding a percentage by how much in percent is this area reducing. Okay, so if area is headed, what was the original one? What was the original area? 43.24 square millimeters, isn't it? So by the end of the test, it has reduced, isn't it? To how much? It's necking. So that reduction in the diameter is known as necking. So we've been told in the question that at the end it had what? Next to an area of, so it had reduced there to 82.3 square millimeters, isn't it? So initially it was at 43. As you are applying force, it's the diameter is reducing, so it becomes a small one at 32.3 millimeters squared. So you're trying to, now you're being asked to find the percentage, okay, by which it reduced. So just mathematically, how do you think the formula looks like? How do you think that formula will look like mathematically? Okay, yeah, it is a minus. So what are we looking at here? We're looking at what we started with, right? Minus the final one and divided by what? Multiplied by, or simply changing area. Sorry. Changing area multiplied by, divided by the original area and multiplied by 100. So the change in area is the difference between what you started with and what you ended up. Quickly, let's find that answer. Twenty-five point 3%, isn't it? Anyone else who found a different answer?
We found 22.1.
How come? Look at your calculations again. You have 43.24 here. 0.24? 43.24 minus 32.3. Then here you have 43.24 multiplied by 100. So you should all find 25.3%. So anything, area reduction above 5%. Okay. Any percent area reduction above 5% concludes that the material is ductile. Okay. So in this case, 25% is way above 5%, isn't it? So we can safely conclude that this material is ductile. All right, it's ductile. It was able to retain, to stretch out quickly, or the diameter was able to decrease, okay, quite well before it fractured. So the difference there in the decrease in diameter was quite big. That signifies that the material was in fact ductile. It wasn't brittle. Okay, let's breathe for 5 minutes and we'll continue and end early. Let's continue and end. Yeah, just realize the recording. Okay, so let's continue. Let's look at another question. Let's forget about all this. Hoping we're clear. Okay, let's look at another question. Okay, so right, question 2. Mr. Sakala. Mr. Sakala. Tested a steel, the metal steel, a steel tensile testing, a tensile specimen. Mr. Sakala tested a steel tensile specimen with a cross-section area of 90 millimeters squared. 90 square millimeters. Okay. The Sakala tested the steel tensile specimen with cross-section area of 90 millimeters squared. To stop. The measure of force at the yield point was 58 kilonewtons, kN, was 58 kN, and the maximum force was 67 kN. Maximum force was 67 kilonewtons. Mr. Sakala tested a steel tensile specimen with a cross-section area of 90 square meters. The measure of force at the yield point was 58 kilonewtons, and the maximum force was 67. Full stop. Help Mr. Sakala calculate. Help Mr. Sakala calculate the following. Number one, yield stress. Number two, yield. So A, what do we have? Yield stress. Then there's also C. Mr. Sakala later measured the force at the limit of proportionality and it was later measured extension and it was 0.12 meters over a given 8. millimeters over a gauge length of 50. Okay. Are done raising your question? This one is A. Calculate A2. Remember what I said about stress? All stress is there. All stress is the same, isn't it? What differs is the type of force. Don't forget that. The formula for stress is the same. We just use they're just different types of stresses. And what makes those stresses different is the type of force. People are stressed different, isn't it? Others it's marital issues, others it's financial, isn't it? But we all call it stress. Sometimes we say financial stress, Shani stress. That's what we're doing here also. We have yield stress. I'm trying to give you pointers. So what are we using for this one? The symbol for stress is sigma. Okay, so what type of stress are we dealing with here? Yield. So even the symbol will change for stress, yield, stress. Okay, so sigma y is equal to F over, that's the general symbol for stress. For us who are calculating only engineering stress, we always use the original cross-sectional area there. What next? So we need to know, for us to be able to calculate this one successfully, we need to be able to know what kind of force we need to apply here. So we need to apply which kind of force? Yield. If we're calculating for proof, we'll look at F at proof. Okay, except for tensile tensile stress, that's when we get the maximum force. Even just the word ultimate, isn't it? Means they're one at the top. So ultimate tensile stress, that's the one that we get F max here. But the denominator is always the same. Okay. So I'm trying to tell you this so that you find it easy to know the formula. Otherwise, you'll be checked out if you try and enter with formula in there. You know the school rules. So you're better off memorizing. I won't given you a simple way to memorize those. So calculate. Tell me what you find for this one. Our class is almost done. Remember, always convert from kilonewtons to what? To newtons. Hmm? 644.4 ME. 644.4 newtons per millimeter squared, isn't it? Or megapascals. That is our answer. How many got that one right? 644.4. What did you find? You can't, it doesn't even deserve to be to be said out. Who found a different answer? I come and look at your working. You found a different answer. Sure. Okay, let's calculate together. What's Fy from the question? So 58 multiplied by 1,000. Yeah, so there was one molecular those that has the wrong answer. I told you, Chisungu. Mechanical properties, Chisungu. Apa ni youth that pene pa ko pepa ko. Huh? Oh, what you seen? Apa ni youth? When you say you, then they say you youth stress. Huh? If say same thing, someone was listing down their stresses, they have financial stress, umuntu monakota financial, marital, tena kwa religious stress. Maybe they are almost chasing you. Financial, yeah, very financial. Let me tell you, start calculate stress ya kwa finances. So monakwa in Congo, isn't it? She are very related to it. Financial stress. So come on for youth point. Can I point now? I'm moving from those two, from the elastic region to that point that we look at. So meaning you're talking about youth. So youth. So meaning youth stress. Right? We've gotten 644. 644. Okay, let's move on. Find the next one. Tensile strength. Remember, I said it can either be ultimate or just tensile strength. It's the same thing. What's the formula? So this is A. Let's come to B. Pardon? Yeah, so sigma, same for all stresses, isn't it? Sigma, except it has what? TS, isn't it? Is equal to F over, all right? So what kind of force are we dealing with? Maximum force to get the ultimate strength. So which one is the maximum force? 67. Okay, so we have 67 kilonewtons. We're going to convert it to newtons by multiplying by 1,000, isn't it? Sorry, here we didn't finish. What was? 99. Then we had our answer. 6.058. Or newtons per. You just simply collect it. Okay. So here we have this multiplied by what? 90. Which is equal to? M A. Capture this one. Oh yeah. Okay, let's go to C. Have you calculated already? Find C. The force at the limit of proportionality. What does that give you? What is the limit of proportionality? What is proportionality? What is proportionality? Where there's a straight line, isn't it? All this is proportionality, right? In short, the elastic region. That's why we have proportionality. Linearity means it's where the straight line is, isn't it? Linearity, proportionality, that is found where? Where we have the straight line. Where do we have the straight line? That's the elastic point. The elastic region. Okay, so now let's look at the question again. Find out what that is. So the force at the limit, so meaning the force where the proportionality is ending, isn't it? The limit. Remember, it has a limit. The limit is what? 53 kilonewtons, isn't it? He later measured the extension. First, he measured the force at the limit of proportionality. So he measured that force where the proportionality is ended, and he found it was what? 53. Right? What else did he do? He later measured the extension. So this is force and this is extension, right? So he measured the extension at that limit. Let's write it down, x-axis. So he measured that x. What value did it give him? 0.12. Okay, are we together? Over a gauge length of 50 millimeters. What is this? Original length, isn't it? Calculate the modulus of elasticity. So what's the data? Let's look at the data. He has what? F, right? At the limit of proportionality, LP is equal to 53 kN. What else is given? Extension, right? At that limit, corresponding extension, that is 0.12 millimeters. What else is given? Original length, which is 50. And you know the formula for flux, isn't it? So what is missing on flux here that we don't have? Original cross-sectional area, you are given L. I have the answer. I have the answer, then we can break it. Yes.
Is it 245.30 gigapascal?
I'll not say yes and who will stop calculating. I want to see everyone. You calculate before I do that. It sounds childish, but it's everyone to understand. This one is also. I need to know what time we need to do tomorrow. Pastor, please help us figure out your time. I meet every day till Friday. Then Sunday, if possible. No, but Sunday, yes, maybe for study. And no study. No study. Split up to Friday. So that you use the weekend to study for your exams. So which topic would you want us to revise? Phase diagrams? Okay, let's look at this diagram tomorrow. Okay, we'll look at that also. Okay. No, everything that we covered is coming. So I just want you to need to know. So I need to hear feedback from you which areas are not covered. Those are the ones that I'm focusing. Everything, even this is coming. Everything.
Sorry, that's the focus on that.
Focus on everything. So you're just telling me where you're not key. Right? You don't want that method. What do you want? So you want me to give you the topics I've been already?
Where we can focus.
No, what I'm not giving you is that there's would have covered it. So I'm going to look at what we covered. Everything. The syllabus is went beyond. You're supposed to look at rules. Types of wood and channel, supposed to look at code breaking, we're supposed to look at diffusion, full time look at diffusion, look at diffusion. So those ones I'm just taking them and they're not coming to the exam. But everything that we're covering, we covered atomic structure, so we covered what? We covered types of materials, ceramics, metals, and those like classification, followed by atomic structure, cellular things, So I remember we had a problem, a challenge, isn't it? These ones. So trying to determine a 100, a 110, the matrices, isn't it? Okay, so now we need to get plans. How many days do we have left? I'm going to say let's maximize out. Go through. I remember there. So atomic structure. Looking at the electron, the type of bonds, that's on the packaging. Was very assignment. Then we looked at the crystallographic planes and points. Well, we're looking at the vectors, isn't it? The x, y. So this is x, that's y, and that's z, isn't it? We're looking at that. So in terms of matrices, I think not, for example, I think don't cover those because a lot of work. But I want you to understand the planes here and the vectors. You should be able to draw the planes and the vectors. And calculations for linear density, planar density, those you need to know. From there, which topic follows? We looked at ferrous and non-ferrous metals. Yeah. That one is easy because it's theory. You need to know which alloy is made out of, the composition of alloys you need to know, and the uses of generally metals. You're supposed to know those. We didn't do corrosion, but I shared most things. So as you can see, corrosion is also under corrosion. I want you to know the 8 classifications. It's 7 or 8 classifications. Okay. We'll just do the theory part, yes. Be able to explain the 8 classifications. If you need maybe a lecture on that, there's some lectures online. Check my channel. And we looked at corrosion there. Okay, so like I'm repeating this. For corrosion, don't look at, there's only one section where I like calculation questions. But let's ignore it. I just need to know the types of corrosion. That's important. You need to know how metals corrode. Better understanding, go to the channel. I think that's where the notes are. Then you have the PowerPoint actually. You have those notes, just go through. They're very well simplified. Mechanical properties, we're doing it now. So we're supposed to look at magnetic properties, but we're not covering that. Okay, that comes aside, forget about it. But electrical properties, let's do a 2-3 questions together on electrical properties. Those are coming in the exam. Electricity.